folks. Review for this Friday, as previously announced. Territory will be over here in Flint, 5150. The room has two different numbers depending upon the level of elevation from which you enter the room, but it's the same room. And let's just make special quiz 3 due on this Friday. Now, if you don't intend to be present at the review, well, you're still obligated to get that special quiz in here, along with the evaluation form for your discussion instructor. If you want to give that to me on Wednesday because you don't want to go to the review, that's fine. But you want credit, you have to submit it ever so obviously. Finals a week from today. Starting at this very, very nice time. Now the official time is 7:30. But I want to give you more time. And this way I'm going to give you more time. So if you don't want to wake up until 7:30, that's your business. But if you want 3 hours to work on the final, be there at 6:30. Where my poor, misfortunate helpers will have their eyes propped open with toothpicks probably, and be ready to get you going on this exam. I'll take advantage of every leeway the university offers me, because they have no business telling me how much time I'm supposed to allocate for an exam. They might as well tell me what's supposed to be on the exam. And then I'll say, you take the exam and pass it, and then I'll let you have a word about it. They will quickly shut up and go away. I guarantee. Final locations, we've been given 2 rooms, little 101, little 109. It's a bit much to squeeze us all into either room. So I'll divide us up by alpha groups. Probably A to L or A to M, something like that, go here and whatever. I'll tell you that on Wednesday. No big deal. Now then, let's get at and complete our conversation on how to develop rationale for strengths of Bronsted-Lowry acids, which, as we have recognized, we do in terms of sizing up the effective negative charge density of the conjugate base of the acid. Because once again, by conjugate theory, when we know the relative strengths of a series of bases, we immediately know the corresponding relative strengths of the conjugate acids of those bases. Charge size ratio, the first factor we looked at, electronegativity, induction. Induction as a function of length of the covalent bond skeleton, where we discovered that induction falls off as the covalent bond skeleton length increases. Orbital electronegativity, resonance. And now, principle of maximum overlap. I again state that as this is discussed in the paragraph on such that's in the notes, that pretty much sums it up. From a theoretical standpoint. And how does the theory come about? By observation. By recognizing. By measuring bond strengths. By studying properties of species like effective resonance and such. Bonds between smaller atoms are generally a good deal stronger than bonds between larger atoms. Bonds between smaller atoms are generally a good deal stronger than a bond between a small atom and a large atom. We're not surprised at this, because in general the smaller atoms have appreciable electronegativity. Upshot, the valence electron density with the smaller atom gets closer to a nucleus of appreciable electronegativity. I mean, even if an atom has an appreciable electronegativity like bromine, that's a big atom. So the valence electron density are not going to be all that effectively stabilized when you consider size. Because the valence electrons will still be rather substantially removed from the protons in the nucleus from a distance standpoint. An example, if you operate on a CO2 molecule and replace one of the peripheral oxygen atoms with a sulfur atom, you get this stuff. I call it the Officers Candidate School molecule, OCS. Its common name is carbonyl sulfide. Its systematic name is something that I find very strange, so I won't even tell you what the systematic name is. You can look it up on Google if you want to. What counts, however, regarding principle of maximum overlap is to recognize the Lewis picture. That's here. The Lewis picture suggests that the oxygen atom and the sulfur atom are each electronically equivalent. They're each connected to the carbon atom with a double bond, and each peripheral atom has two non-bonding pairs in a so-called octet. You think these bond lengths and strengths are the same? How do you think they compare? Which bond is stronger? CO or CS? CO, a hell of a lot stronger. I looked at the data yesterday. I didn't get a chance to write it down, but that's not of consequence. What counts is to realize this bond is a hell of a lot stronger than this bond. In fact, the chemistry that this thing shows when it reacts is to keep this bond intact. One reaction shown by this is to lose sulfur and convert this to a CO triple bond and convert this part of the molecule to carbon monoxide. Or if you react this with oxygen, this bond breaks and you wind up making CO2. Those are the principal chemistry shown by this molecule. Illustrates the point. This atom is not only more electronegative than this atom is size-wise rather similar to carbon, whereas this atom is a lot bigger. Upshot, you get much more effective orbital overlap between these atoms, which strengthens the bond. Now then, back to nitric acid, which has a considerably greater Ka than chloric acid. Here's the conjugate base of chloric acid, the conjugate base of nitric acid. We looked at these last time. And so far, it appears that, at the minimum, the effective negative charge density of this base should be at least as small as the effective negative charge density of this base. Each bears a total charge of -1. Each has 3 peripheral oxygen atoms to stabilize negative charge density effectively by induction. Each has a central atom of appreciable electronegativity. And some tables show chlorine to be a slightly more electronegative atom than nitrogen, but let's take them as the same. And chlorine is a good deal larger than nitrogen. So if I'm stabilizing electron density here as effectively by induction as I am here, and as effectively by resonance as I am here, then I'm effectively smearing this single unit of minus charge over a larger surface because chlorine's a bigger atom than nitrogen. Upshot, this would have a smaller effective negative charge density than this, which would make this the stronger acid, but that doesn't fit the facts. So something's got to be followed up with this explanation. Or at the minimum, incomplete. Now then, look at those 2 anions. Junk in the eye. How do the hybridizations for the central atoms compare?
and that trades sp2 would be chlorate sp3.
Mm-hmm. Now, with that, you should immediately be able to get at the geometry of this versus the geometry of this. How do the geometries compare? I'm listening.
Trigonoplanar versus tetrahedral?
Well, it can't be tetrahedral without 4 peripheral atoms. Well, what is it then? Trigonal pyramidal. Okay? So this is trig-planar. This is trig-pyramidal. What impact or effect does that exert on bonding, if any? Let's take a look at a model. Uh-oh. This is a model of nitrate ion. The blue atom, which I hold, is the central nitrogen atom. 3 black peripheral atoms represent the peripheral oxygen atoms. What do the loops simulate? These figure 8 loops. What?
Lone parallel.
What does this illustration show? Do you remember the shapes of orbitals, which presumably you learned about in 2045? What does this model represent? This is a p orbital sublevel, with each individual p orbital looking like, as I choose to describe it, a 3-dimensional figure 8. You want to use a different description? I don't care. But here's a single p orbital. Which one is this p orbital? Because how do the p orbitals geometrically compare? They all look alike, but one has its lobes lying on this axis, another has its lobes lying on this, the vertical axis, and the third and remaining p orbital has its lobes lying on this axis, which, as I stand, has one end of the axis pointing at me and away from you, and the other end of the axis pointing away from me and toward you. So how do we usually label these orbitals? We use Cartesian coordinate reference axis set, x, y, z. You've heard about this. What's the geometric significance of x, y, z Cartesian coordinate reference axes? There are 3 straight lines which intersect at a place in space we call the origin. And how geometrically do these 3 straight lines compare? They are mutually perpendicular, aren't they? Bingo. And this direction we usually take as which direction? X. Doesn't have to be. I could call it X or Q or Z or who cares? I can call it anything I want. But I'm going to call it X. So let's agree to call this direction X. Now then, what do you want to call this direction? Now wait, because I know in geometry class you likely call this the Y direction, because for the most part in geometry class, especially plane geometry, you're looking at everything in 2 dimensions. And so the reference axes you referred to were X and Y. So you had the x-axis going this way and the y-axis going this way. But in chemistry, where we're dealing with 3 dimensions, chemists, for reasons I really don't know, but chemists have decided this is the z-axis, not the y-axis. I don't know why. But if you're going to look at chemistry books, they're going to up and down direction is z. So learn it, so you can understand this stuff when you read it. Which means by default, this p orbital, which has its lobes skewered right through the middle by this axis, the axis which projects towards you and away from me and toward me and away from you simultaneously, is py. Right? And again, this shows the sublevel, the entire p sublevel. The p orbital on the x-axis, y-axis, z-axis. All right? Now then. px orbital. py orbital. Can these two p orbitals, this p orbital belonging to the atom represented by my right hand, this p orbital belonging to the atom represented by my left hand, can these p orbitals overlap with each other to make a pi bond? Px on this atom, py on this atom? No. All right, I'm going to turn this to pz. Can pz on this atom overlap with py on this atom to make a pi bond? No. What orbital does this atom have to use if it's going to make a pi bond with this atom, if this atom is going to use pz? Which one? P what? Z. Z. Because now the orbital lobes are mutually parallel. Upshot, when the atoms approach, the top and bottom lobes for each of these pz orbitals can overlap with each other and make a pi bond. Do you know what pi bond means in terms of regions of overlap? Did you learn that? What's the difference between a sigma bond and a pi bond? How many regions of overlap? For a sigma bond, 1. For a pi bond, 2. Now then, did you learn anything in 2045 about the shapes of d orbitals? There's an illustration of d orbitals in the notes in chapter 24. I forget the page, but you can look at it if it's necessary. 4 of the 5 d orbitals look just like this. Can a d orbital make a pi bond? What do you think? Oop, I picked the wrong one. This one won't pull out of the base. That look like a pi bond? That give you 2 regions of orbital overlap? You betcha. Now what if a d orbital that looks just like this is oriented in space this way? And a d orbital which looks just like this and is oriented in space the same way on an atom over here, I should have brought the other model, meets up with, how many overlap regions will we have? 4. That's called a delta bond. Just language. Sigma bond, 1 overlap region. Pi bond, 2 overlap regions. And delta bond, 4 overlap regions. Nothing fancy about it, really. And here I've drawn an illustration of effective pi overlap between 2 p orbitals. Pardon my lousy artwork. There is more or less effective pi overlap between a d orbital and a p orbital. We just showed you with the models. Now then, is that kind of overlap achievable with the nitrate ion? With each component atom being sp2 hybridized, which means each component atom has got a p orbital available for pi bond formation. And since this thing is planar, the sigma electron density is in this plane, which contains the nitrogen atom, the oxygen, oxygen, oxygen peripheral atom. They're all in this plane. Okay? Where's the pi electron density? It's up here as well as down here, because this p orbital on this peripheralized atom is overlapped here like this. Same thing for this and for this. Upshot. With nitrate ion, because of its planarity, all the p orbitals of its component atoms have lobes which are mutually, what? Parallel. And that way you can get effective orbital overlap and generate a strong pi system. Now then, let's take a look at chlorate ion, which is not planar. It's pyramidal. This simulates a partial orbital lobe on the central chlorine atom. It's easier this way. Nitrate ion's getting mad at me because I'm breaking its bonds. Given that this is trigonal pyramidal, can I generate effective pi overlap like that? No. Because the lobes of the orbitals required to generate or construct a pi system cannot be mutually parallel. Problem. Do you think this Lewis picture, which is the best Lewis picture we can write for chlorate ion, since it minimizes formal charge distribution, but also implies substantial pi bonding and resonance? Do you think this Lewis picture is a reasonably accurate representation of the valence electron environment of a chlorate ion? No. But this one is, because this is planar. So, we recognized here a case where Lewis picture construction can lie to you and deceive you. Now, what would you do to get an answer to this question? The question being, how does the strength of a ClO bond in something like chlorate ion compare to the strength of an NO bond in something like nitrate ion? What would you go after to find out about pi bonding being stronger in nitrate ion or pi bonding being stronger in chlorate ion? What property of these species would you look for to answer the question? Which shows stronger bonding? How about bond strengths? Huh? Nothing fancy about that, is there? We see if we can find data for an NO bond and its strength in nitrate ion and compare that to the strength of a ClO bond in something like chlorate ion. And if you look at the information available, you'll find the NO bond is a lot stronger. Now, there comes a problem with deciding whether or not there is any pi stabilization of the chlorine-oxygen bonds in something like chlorate ion. See, for nitrate ion, we can make species containing nitrogen-oxygen bonds, which we know for sure have 4/3 bond order, like this, 3/2 bond order, like nitrite ion, bond order of 2 for an NO double bond, bond order of 1 for an actual NO single bond. We can make all those species and then measure the bond strengths. But you can't make any species, at least none of which I am aware, where we know for sure we got a chlorine-oxygen single bond. Because all the chlorine-oxygen bonds and all the materials containing chlorine-oxygen bonds resemble the kind of bonds you have here in this. So am I looking at a bond which has pi character? It's hard to tell. There are other ways we could pursue this, but we'll not concern ourselves with these possibilities at this stage of the game. So, PMO. More effective orbital overlap here. These atoms are similar in size. These atoms are rather dissimilar in size. And this thing is planar to allow effective p orbital overlap to make an effective pi system. as opposed to this, which is not planar. Now you got to be careful. We're always trying to make generalizations whenever we can, and provided they hold. But you got to be careful about these generalizations, because as you go deeper and deeper in chemistry, and likely you folks have already realized this, whenever you are comparing the chemistry of two different species, they will never be the same. Never. So sooner or later you're going to find significant differences, or at least differences, in the chemistry of two different species. Has to be. So you're going to look for exceptions to generalities. Now here, perchloric acid. The last statement there. But Ka perchloric acid is considerably greater than Ka nitric acid. In fact, if you recall in our acid-base table, which acid is at the top? That's the one, perchloric acid. Okay? Well, there's a model of the perchlorate anion. Again, this thing is tetrahedral, perfectly so. You can't have an effective pi system like you have in something like nitrate ion. And you're going to deal with this in organic class all the time. In order for a species to have effective resonance, it's got to be planar, and it's got to have a composite of sp2 hybridized orbitals, so you have these available p orbitals for pi bonding with their lobes, orbital lobes, mutually parallel. But this thing is a weaker base, a more stable base than nitrate ion. So now it must be the case that when you build up induction stabilization by adding an additional peripheral oxygen atom, that wins out. The facts speak for themselves. Perchloric acid is a stronger acid than chloric acid. You know, which based on resonance considerations you wouldn't expect, but based on induction considerations you would expect. And here the induction wins out. Well, how about Ka perchloric versus Ka perbromic. How do you think these Kas will compare? Well, for starters, would you bet the Ka values are close? Close? Bromine, same chemical family as chlorine. And on tables which show chlorine electronegativity is 3.0, those tables also show bromine electronegativity is 2.8. Not a whole lot of difference. Okay. So how do you think the Ka values will compare? Well, based on size, I'm smearing the negative charge over a larger surface still when I change the central atom from chlorine to bromine. But don't forget PMO. Between which atom pair, chlorine oxygen versus bromine oxygen, shall I expect stronger bonding? Chlorine oxygen, bromine oxygen? Chlorine oxygen. Now look that up. That's true. The chlorine oxygen bonds stronger than the bromine oxygen bond, but not by a hell of a lot. It's about 4 kilocalories per mole. That's not a lot. When you put in a mole, that's Avogadro's number of bonds. Okay? But it's still stronger. And as it turns out, that's all I can say in a case like this, because I don't see how you could predict this absolutely and correctly. As it turns out, Ka for perchloric is a little bit bigger than Ka for perbromic. This is a somewhat stronger acid than this, but they're both exceptionally strong acids. I'm sure this is a good deal stronger acid than nitric. Okay? Now then, one more question. If I consider pi bonding in this dichlorate ion. Or this, if I take this to be a model of perchlorate ion, where I've added an additional peripheral oxygen atom. If there is pi bonding, what orbital or orbitals is the central chlorine atom using to make pi bonds with the peripheral oxygen atoms? I'm listening. P orbitals? P orbitals are used up in the sp3 hybrid. So what orbitals will remain? Can't make pi bonds with s orbitals. So it must be d orbitals. Has chlorine got valence d orbitals? Has chlorine got valence d orbitals? Yes or no?
Yes.
You're damn right it does. But the chlorine valence d orbitals are what? Occupied with electrons for the chlorine atom or empty? Empty. So, chemists often refer to pi bonding between an oxygen atom and an atom like chlorine as p pi to d pi. P pi to d pi. Because the oxygen atom takes electron density, which was previously considered non-bonding, but advances it to bonding status. So the oxygen atom, because of its non-bonding electron density, supplies electron density, converts it from non-bonding status to bonding electron status, and therefore supplies the electron density to make the pi bond. P pi 2, because this supplied the electron density, to d pi. Because this orbital on the central chlorine atom accepted the electron density. Supplied the electron density, accepted the electron density, that's why the arrow points this way. What kind of bond formation interaction does that sound like? What's this p pi to d pi bond formation business a takeoff on? Lewis acid, Lewis base chemistry? That's what it is. Coordinate covalent bonding, that's all it is. Okay? Lewis. Lewis base, Lewis acid. All right? Now then, solvation. Now keep in mind the word is solvation, not salvation. I don't know how to provide you with that attribute. It's really not all that important, this consideration for us, because practically speaking, we're doing all our chemistry in the same solvent. But when you start studying acid strengths in different solvents, you'll find out that solvation plays a big role. For example, if we consider Ka for acetic acid in water, which is 1.8 times 10 to minus 5, and compare it to its exhibited Ka value in a solvent like ethanol. How do you think Ka for acetic acid in ethanol will compare to 1.8 times 10 to minus 5? Here's the ionization equilibrium, as we've looked at many times before, established by dissolving acetic acid in water. There's the acetate anion. Negative charge density stabilized by oxygen atom induction, stabilized by resonance. And what else will stabilize this negative charge density? Now think about the solvent. Oh, and of course hydronium ion. Now, in ethanol, the acetic acid molecule has no choice but to protonate ethanol. And we talked about that way back in chapter 18. What component atom of ethanol will accept H+ if it reacts with acetic acid? The oxygen atom. So, still making the acetate ion. But now we're going to make this. What's its name? I don't know. I don't give a damn. Which process do you think is the more favored process? That's the process for which the K value will be larger. The first process is Ka for acetic acid, which is 1.8 times 10 to minus 5. How do you think Ka for ethanol, for acetic acid and ethanol compares to 1.8 times 10 to minus 5? Three possibilities. Bigger, smaller, or the same? And I bet you won't bet the same. That's good because it's not the same. Ka for this process, bigger or smaller than 1.8 times 10 to minus 5? Ah, we sound like we have got an argument here. How many say bigger? Come on, stick up your hands boldly and proudly. How many say smaller? How many didn't vote? 8 million points off the final for not voting. Don't even bother to get up. Won't do you any good. Final will not be worth 8 million. Or if it was, you'd be even. You'd get a 0 with a perfect score. The answer is Ka for acetic in water is a good deal larger than Ka for acetic in ethanol. Why? Because you know that's what counts. I don't give a damn about your votes. Other than I can make you pay for beer and pizza. Why? Water is? Oh, I don't know about that part.
The product is unstable.
Considerably more polar, electric, because each of these reactions make ions, don't they? And in which solvent do you think you can more effectively stabilize the presence of ions? Water, the more electric, the more polar solvent, or ethanol, the less electric, less polar solvent? Water, that's right. That's the difference. If you run the ionization reaction of acetic acid in a solvent with a low dielectric constant, that's a solvent with a low polarity, you'll find out that the tendency of acetic acid to react in that solvent by ionization is pretty damn small. The Ka value will be very small. All right? And now oxidation state of central atom. The last factor to be added to this bag of tricks. So look at this big bag of tricks you got to think about when I'm asking you questions about this stuff on the final. And I trust by now you've recognized that the arguments which you get from this bag of tricks as applied to a particular species don't always point in the same direction. Like for HF versus HCl, where the corresponding bases are fluoride ion and chloride ion. If I'm going to argue that fluoride ion stabilizes negative charge density better than chloride ion because fluoride ion is more electronegative, which is true, I would argue that HF is a stronger acid than HCl, and I'd be dead wrong. So I got to go someplace else. So I pay attention to negative charge density stabilization as a function of charge to size ratio. Chloride ion, fluoride ion. And now I'm concentrating the charge much more on the much smaller fluoride ion. Does that fit the facts? Does that make fluoride ion a stronger base than chloride ion? Yes, because fluoride ion is a stronger base than chloride ion. But when I go to HF versus water, for which the conjugate bases are hydroxide ion and fluoride ion respectively, now I'm looking at hydroxide ion, which is a larger species than fluoride ion. Not a whole lot larger, but larger. So on the basis of effective negative charge density, summed up as a consequence of charge to size ratio, I'm going to say hydroxide ion is a weaker and more stable base than fluoride ion because the hydroxide ion has a single unit of minus charge on a larger surface. And I'll be wrong. So now I better look someplace else. Now I'll look at electronegativity. Here electronegativity supports the case. In the case of HCl, HF, charge to size ratio supports the case. So keep in mind, oftentimes, from this bag of tricks, you'll get opposing conclusions. And which conclusions do you pick? The ones that fit the facts. That's all you can do. Because the only bottom line dictator is what is true. And what is true in science class is that which is supported by experimentation. The results of carefully made measurements. What are the facts? For example, we told you about this PMO stuff. I went to OCS because it so nicely fits the facts. Sulfur being a lot larger atom than oxygen. Now then, example for this last case. Where did I put it? There it is. This is 9. Nitrous acid strength versus sulfurous acid strength. Now notice I purposely wrote quotes on the H2SO3 formula because that's the way the textbooks write that. Now what's the first thing you have to do to go after this issue? What is it? Lewis structure of the conjugate base. Get at it right now, quick, boom. You got 30 seconds, if that. And that's only if I'm in a good mood. If I'm in a nasty, selfish, greedy mood, I'll give you 10 seconds. That's it. Because by now you should be whiz-bangs at writing these Lewis pictures. Did you get these? Can I improve this Lewis picture? Let's take minus and move it toward plus. Zip, just like that. All right, I'm going to take this one, put it there. That takes away that minus charge and takes away that plus charge. For which of these do you expect a more effective resonance stabilization of negative charge density? For which one? Nitride ion? That's trigonal parameter. Now then, for which of these do you expect a more effective negative charge density stabilization as a consequence of the presence of peripheral oxygen atoms? Is this a peripheral oxygen atom? Is this a peripheral oxygen atom? No, it's a skeletal oxygen atom. This is not an oxo-oxygen. This has got a hydrogen atom bonded to it. Such atoms are not particularly effective at stabilizing negative charge density. Not like true oxo-oxygens. So in sum, these are going to stabilize negative charge density by induction to about the same extent. So, which is the weaker base? I'm expecting better resonance here. But is this portion of this species planar? Can any three atoms be contained in a plane? Can any 3 points in space be contained in a plane? Yes. So I can look at that as having a degree of planarity, even though this is sp3 hybridized and this is sp2. Which is the stronger acid, this or this? Now let's give you the facts. Let's write this down. Okay, 1.3 times 10 to the minus 2. Ka is 7.2 times 10 to the minus 4. Ha ha, that's a lot stronger acid. Now, what if I go at the central atom, peripheral oxygen atom bond strengths based on the oxidation state of the central atom? Now what might I expect? Nitrogen atom oxidation state? Oxidation state? What is it? Plus 3. Sulfur? What is it? We played this game. Chop, chop, chop. 6 less 2 plus 4. Chop, chop. 5 minus 2 plus 3. This has a higher oxidation state. Do you believe that has an impact on bond strength? What will be the impact? I've got a plus 4 oxidation state sulfur versus a plus 3 oxidation state nitrogen being bound to the same atom. Where do you think I'll have the stronger bonds? Plus 4. Does that fit the facts? Yep. Okay. Tomorrow, more stuff on this in discussion, and of course, we finish on